convergence. Now we're next to the division of power series. We have just looked at the multiplication of a power series till now, but we can handle division of a power series in a similar way. So just let's assume that f of g and g of g denote the sums of series 1. That is, f of g given by this series, which has a coefficient an, and g of g given by this series expansion, which has a coefficient bn. And suppose that we consider the division. We do not want the singularity by construction, so we exclude the case g of g is equal to 0 when the modulus of g negative g naught is less than larger. Since the coefficient f of g divided by g of g is analytic throughout the disk, f modulus g negative g naught is less than larger, it has a series representation. Okay, so we can express this quotient function by using this power series, which has coefficient dn. In this case, we denote the coefficient dn. Dn can be found by differentiating f of g divided by g of g successively and evaluating the derivatives at g naught. The first three coefficients in series 2 are given by the equation as follows. This series 2 means. So let us compute the first few coefficients of large f of g given by this. There is a small f of g divided by a small g of g by differentiating it. So first, large f of g naught is small f of g naught times g of g naught. So we get this for the coefficient c0. Large f and zeroth derivative means that just original function means that. So we get this large f of g naught because 0 factorial is 1, which means that, sorry, this is typo, small f of g naught divided by g of g naught, which is exactly a0 times b0 because we consider this a series expansion. And then next move to the computation of c1 here. To compute it, we need to first derivative of large f here. The first derivative of large f is computed by using the differentiation rule for the quotient function, and we get this. Yes, f prime g times g of g negative f of g times g of g divided by g squared here when g is g naught. So we get, in this case, we need to divide by 1 factorial here, but 1 factorial is 1, so we just get the first derivative of large f of g naught. And so we get the same value of f prime, large f prime g naught. Then we know that small f prime g naught is a1, and g of g naught is b1, and f of g naught a0, and g prime g naught is b1. So a1 times b0 negative a0 times b1 divided by because g naught g of g naught is equal to b0, so for the denominator it's the same to b0 squared here. So we get this. Similar to the case of multiplication of power series, in this case, the results are the same as those found by formally carrying out the division of the first of series 1 by the second. You can see this formula. Since it is usually only the first few terms that are needed in practice, this method is not difficult. You just carrying out the division by using the pencil. So let's check it the example 2 for what the just explanation means here. As pointed out in section 39, the zeros of entire function hyperbolic sine g are the numbers g is n pi I. Here n goes from 0 to infinity in both directions. That means that so n could be plus minus 1, plus minus 2, yeah, integers. The problem is to find the first few non-zero terms of 1 over hyperbolic sine g here. The reciprocal 1 over hyperbolic sine g is expressed by this, because hyperbolic sine g has the Taylor series, this. So 1 over g plus 1 over 3 factorial times g cubed plus 1 over 5 factorial times g to the power of 5 and plus keep going this, which can be written, just pull out 1 over g from this expression, then which is written like this: 1 over g times 1 over g, 1 plus 1 over 3 factorial g squared plus 1 over 5 factorial g force plus. It has a Laurent series representation in the functional disk given by this. The modulus of g is greater than 0 and less than 5. A power series representation of the function in parentheses here can be found by dividing the series in the denominator int unity as follows. Just look at what happened here. Yeah, quite easy works. Here you put the unity here and then denominator here, just to cancel this first term 1 and write here 1, then the result multiplied by 2 terms here, 1 and these terms, you just write here. Second line, you can see the result that here the first term is 1 and second term is 1 over 3 factorial g squared here, and like this. And then subtract the first line and the second line here, then you get this result here. And you just consider to cancel this first term here by multiplying this and something here. You just write here. In this case, just negative 1 over 3 factorial g squared here. Then we get this for the first term here. The second is just multiplied by this. These 2 terms here, we get this. Negative 1 over 3 factorial squared times g first. g to the power of 4th here, then subtract this line from the first line here, and you get this. So similar way you do, then you get this result for the 1 over hyperplus ing. Oh, sorry, here. Oh, for not hyperplus ing, just for this function. Then we need to multiply 1 over g here. 1 over g here. Okay, then compute the coefficient. Then you get this result. Then in the previous expression, we need to multiply these two terms here, 1 over g and this term. In this case, 1 over g times this term, 1 negative 1 over 6 g squared plus 7 over 360 g to the 4. Then we get this 1 over g negative 1 over 6g, 6 times g, and like this. Here, although we have given only the first 3 non-zero terms of this Laurent series, any number of terms can be found by computing the division.